Hello, and welcome to the new stream. Andrew's just sent a message. I can hear someone typing. That would have been me in the background. So, we haven't done a science stream in a while, and I didn't give people much notice for this one. So I don't think there'll probably be many people turning up for this stream, but that's okay. We can still mess around, play around with some data. And anyone who's here at the moment can of course ask me whatever questions they want. And if people watching later on have questions, they can also leave them in the comments, and I'll try and answer them as best as I can. So, the objective of today is to mess around and look at some data from the TESS satellite, which orbits around the Earth, between the Earth and Moon, and it has observed the largest object in the asteroid belt, Ceres. So I want to see what Ceres is doing, and see if there's anything interesting that can be found from that data. Now, I'm not too sure what my internet quality is going to be like. I suspect it's not so good, which is why I haven't done too many streams recently, because my internet here in New Zealand is pretty bad at the best of times and quite horrible at the worst of times. So hopefully we've got a better occasion at the moment. But yeah, as I said, if you have any questions while you're watching this, leave those questions in the comments, and I'll try my best to answer them. There is a bit of a delay between what you see on stream and what I'm talking about, so there will be a bit of a delay between me answering questions. So anyway, before we get started, let's do what every good researcher should do before approaching a new idea, is to go to Wikipedia. And Wikipedia has in it a wealth of information, and today's information is we need to learn a little bit about what Ceres is before we try and understand what we might be seeing in the data. So, what is Ceres? Well, it says here it's the largest astronomical object in the asteroid belt, which lies between Mars and Jupiter, and was discovered quite a long time ago, in 1801. And this story might seem familiar to some of you. It was originally considered a planet, and then it was reclassified in the 1850s as an asteroid. Oh no, I see. Nice slideshow we have here. That's not a good sign. It may be that my internet just isn't good enough to do live streams. In which case, that would be a massive pain. Let me see if I can make it so it's not a slideshow. Okay, I'm smooth now. Alright, well, just let me know if it becomes unbearable, and we'll see what I can do. I'm not sure I can do too much, to be honest, but we'll see. Hopefully it's not too bad. Okay, so back to Ceres. So it was originally considered a planet and then reclassified. So this will seem very familiar to you if you've ever heard of the dwarf planet Pluto. That was, of course, discovered and considered to be a planet. And then after some time in the early 2000s, astronomers reclassified it as a dwarf planet. But Ceres was reclassified in the 1850s as an asteroid. As they discovered more and more of the objects in the asteroid belt, Ceres looked more like an asteroid than like the other planets. But as Pluto was discovered and a whole lot of other dwarf planets were discovered, it seemed more likely that Ceres was a dwarf planet rather than an asteroid, because it was so big, as we can see in this figure, this nice picture, so big that it's very round and it's got lots of crater marks on it. It's also got some interesting features on its surface, some brighter white patches on the surface. So Ceres is an interesting place. It's not like an asteroid, and this is something that I've learned recently. Ceres is actually probably not from the asteroid belt itself. So Ceres is a rather large object, and it's in the asteroid belt, so you would think that, oh, it's just a very big asteroid. It's like the planet that failed to form in the asteroid belt because Jupiter got its grubby mass on it and held on to everything and stopped stuff colliding and making a new planet. But the reality is, Ceres has a completely different composition to what asteroids actually have. And it's more like the objects we see at the edge of the solar system. So it's what we would consider to be more like, say, the icy things at the edge of the solar system. And this has some interesting consequences, mainly for the origin of these bright white spots. And we'll need to think about these bright white spots in a bit, because they play a role in the data that we're going to be looking at soon. So that's kind of a brief overview of Ceres. The other thing that matters for us is that it rotates on its axis about once every 9 hours and 4 or so minutes or something like that. So relatively quickly, and it's of course an interesting place. So, with the preamble of Ceres out of the way, unless there's any questions about Ceres itself, which we might need to go to Wikipedia to answer for us, because I'm not too much of an expert, or not an expert at all in Ceres. Let's go over to look at the data. So generally I use Jupyter notebooks for the stuff I do. They're very handy, and they use Python, and I can just hack away at it and make an awfully messy notebook until it looks okay. Then I'll try and take functions that are useful and put them into their own classes and objects so that I can use them easier later on. So let's restart this and see what we have. So there are... Stream just died. Okay, maybe my internet is too slow. Let me see if I can... The stream is still being buggy. Let me see if I can swap and become slightly better. Okay. So let's see if this is any better. So hopefully the stream's still alive. I just swapped some stuff around and maybe it'll be a little bit better now. I'm not sure though. Okay, so what do we have here in this notebook? We have some stuff at the front, just importing some packages that we'll hopefully use later on. And then this part here, LC, that's an abbreviation of the word light curve, which I use an awful lot. When we're loading in this data here, which is a light curve I made of Ceres that was observed by the Transiting Exoplanet Survey satellite, which orbits between the Earth and Moon and takes images very often of large parts of the sky. So some of the things that TESS does really well is looking for planets around other stars, but because it looks at enormous chunks of the sky, you can look for anything in that that falls in TESS's enormous field of view, and you can get some pretty interesting data on it. So let's look at this thing I call LC and see what it is. So we'll just plot that here. Let's see. Oops. Okay. So we have this graph here, which looks interesting. It doesn't look like nothing, so that's always a good start. So along the x-axis we have time, but this is time measured in strange astronomy units, so it's in terms of modified Julian date, which is essentially you pick a day, or astronomers picked a day, and they said that's 0 time, and then every day after that day adds 1 to the Julian date. So the difference between 59088 and 59089 is 1 day difference. So it's a relatively straightforward date system, and it doesn't get confused by people having their own local times and all of that kind of stuff. So it's very useful for astronomers to have this kind of formatted date system. And along the y-axis we have how bright the object is. So if you're lower down on the y-axis, you're fainter. If you're brighter on the y-axis, you're brighter. And same thing, if you move from left to right on the plot, you move from earlier times to later times. So what does this plot show us? Well, it shows us that the brightness of Ceres changes over time. If Ceres was a pretty boring object, you would see just a flat line, constant brightness continuously, which wouldn't be really much to look at. But what we do have is some changes in Ceres' brightness. And it looks like a pretty big change here, but in reality it's not too much of a change. It's probably a change that you wouldn't be able to see too much with your own eye if you're looking through a telescope. So TESS is a very sensitive instrument, and it can do some really interesting science. Anyway, let's zoom in to one of these data segments and see what it looks like. So it looks kind of interesting. It's not a flat line like I said before, but it seems to repeat itself. It bounces up and down pretty often. And it changes in brightness in a very particular way. Now this is quite interesting because Ceres doesn't produce its own light. So stars can change in their brightness, they can wiggle up and down, but that's pretty easy to understand because a star makes its own light. It can generate light, and it can you can see how those variations and how it generates light play out in its brightness. But for Ceres, it doesn't make light, it just reflects light from the sun. So any variations that happen in the brightness of Ceres can't be from its own internal process. You could suggest that, or maybe we're seeing the sun's process of brightening and dimming being reflected in Ceres. But this isn't the case. The sun is incredibly constant, or relatively constant for... Depends who you ask, I guess, is the answer here. So the sun, for our purposes, is incredibly constant in its brightness. If you were to ask an astronomer who looks at subtle variations of light from stars, how they pulsate, then the sun is a pretty interesting object and changes a reasonable amount. But for our purposes, it doesn't change at all. So this change in brightness is entirely connected to Ceres itself. And the reason it changes in brightness is quite interesting, I think. So let's go to this thing here, Eyes on the Solar System, which is a great thing produced by NASA JPL to give us all of the data we can see on solar system objects. So let's go over to Ceres. And look at its surface. So you can see that Ceres is a place that's covered in asteroid marks, but it's also got some brighter features on it. So this part here looks a bit brighter Then say the surrounding features. Maybe this part here looks a bit darker than the surrounding features. So we can go around Ceres and we can think about how bright it would be. Oh man, this is really turning upside down. Let me see if I can... I haven't used this program too much before, so let me see if I can reorient ourselves so that we're not kind of spinning all over the place. Well, let's make Ceres spin at least at a reasonable rate. So let's just sit here, kind of looking edge on to the solar system, and see what we see. So you might be able to see there are large chunks of the surface that don't look like much, and then there are parts that look a little brighter. Let's speed this up a little bit more. Like this part's very bright, and then not so much happening around here. And then we get this part is a little bit bright, this part is a little bit bright, and this part again is very bright. So, depending on which way around we are, this can tell us stuff about what we're seeing in the test data. So let's pause that rotation for now, and we'll try and work out which way, if we're above or below the solar system. Trying to find out which way north is. Okay, I think we're above the solar system. Okay, good. This is why you should always play around with things before you before you go live with them, because they'll always be puzzling. Okay, so anyway, these changing surface features change the brightness of Ceres because this part here reflects more light than the surrounding area. And a lot of these images here were obtained with the Dawn spacecraft, which visited Ceres last decade. And Dawn took a lot of pictures of Ceres' surface, but as it was approaching Ceres, it saw that there were brighter patches, or some really bright spots, shining incredibly brightly. Some people suggested, oh, maybe we've detected alien cities sitting on the surface of Ceres. But that unfortunately didn't prove to be true. It turned out to be more like salt on the surface of Ceres. So Ceres has a pretty interesting structure where the top layer is kind of this dirty, gravelly, icy stuff, and beneath that we think that there's like lots of salty, briny water. And every now and then the surface can rupture, and you can get this salty, briny water spraying out onto the surface and creating these bright white surface features like we see here. So instead of alien cities, we found that there's salt. But this is also interesting because it indicates that Ceres is kind of active, and it has things called cryovolcanism. So that is the reason why we end up with this variation in brightness, or at least it's a reason we could say is what's happening. So let's look at something that can tell us perhaps a little bit more about what we're seeing here. Let me just type out some functions. Okay. So I've just taken that data that we plotted here before and put it into another framework. And let's call another thing Periodogram. Okay, so now we've taken that light curve and we've put it into something called a periodogram. So it's essentially like taking the Fourier transform of this data, and the Fourier transform of data is like saying, oh, how can you reconstruct this data by just using sine waves? And the bigger the sine wave is, the bigger the power of it is in the plot we're going to see in just a moment. So let's plot the periodogram. And what we have here is a very strange looking plot, but along the y-axis we have power in terms of electrons per second. So this doesn't really matter so much. You can kind of think of it like, how important is this? And along the x-axis we have the frequency, and this is in terms of 1/days. So if you have 10, that means there are 10 times this happens every day. So we can see that there is a pretty big spike right here around 2-ish days. So around 2-ish times a day, between 2 and 3 times a day, this thing happens. And as it turns out, if we record, what is this value? 2.65. If we do 1/2.65, we get 0.377. So that's 0.377 of a day. So if we want in terms of hours, we multiply it by 24. And what does that get us? It gets us 9 hours and a bit. If you remember before, I said that Ceres has a rotational period of around about 9 hours. So this looks pretty good. It looks like we've found the rotational period of Ceres from this data. So this 9-hour period is this one here, which starts at, say, this point and ends at this point over here. So this is one complete rotation of Ceres from trough to trough. So then the thing is, well, if we start from here and go up to here, what are we actually seeing? And this is something that we can look at now. So let's say we zoom in on this peak here and find out what the time is at this peak. So this is going to be in terms of modified Julian date, so 248711. So let's go down here, write that down, 248711. So that's the time that we're interested in. Now, what do we want to do? We want to do from astropy import time. There we go. So we have time of. Now we need to work out what the format is. So it's 248711. Now I can't ever remember how all of these things work, so let's look at the definitions for these parameters. Scale is fine. Format, I think maybe we want to say format is MJD. Let's try that. MJD, does this give us an error? Nope, that gives us what we want. Okay. So let's call this time peak is equal to that. Okay. So let us convert this to how do you do this again? I think I am going to need to go to the Wikipedia page for this. Astropy time. Why is this? Can I just do 2 UTC? No, I can't. Let me see. There probably isn't a 2 there, it's just UTC. It already is in UTC apparently. Perhaps we want this date. Nope. I don't think we want that. Let me just check this was the right number. It wasn't, so it should be 59088. That's why it's giving me the wrong number. 59088. Okay, this makes more sense. We had definitely the wrong number in there before. I put in the y value instead of the x value. These things happen. So, what we want to do is check 2020 827 on this thing. So on this thing you can put in the times that you want. 2020 8, which is August, and 27. Okay, but since it spins so quickly, okay, yeah, that should be fine. So this is now set to the time when TESS was observing Ceres at its peak brightness. And what do we find? That this thing is sitting right in the middle. So this object right here is sitting in the middle. Now let's see what happens if we get time to play out a little bit faster. And we'll start spinning. Okay, so it's starting to spin. So this is when it's brightest in test data. So now it's starting to rotate away, so we're not getting as much light reflected directly back at us. So we can say we're at this part, the decline of the big peak. And now that it's almost gone, we've almost lost that big peak. You can see that some other bright features have rotated into view as well, but they don't look as bright as the one that's just rotated away. So we might be in this part where we're at this kind of secondary peak now. And now these ones are starting to rotate away, and we're losing their brightness. So, but maybe we're still in this part because it looks like there's another big bright object coming up. So maybe this one here is actually the second bright object that we're seeing. So I haven't looked at this before, so this is kind of guesswork from me as well as from you if you're watching this. So it's strange though, because to my eye this one looks brighter than the one that we started with. So let's see if this time coincides with the secondary peak. This one's going to be a little bit looser because it's not as well defined. Let's just say this time 59088.1273. 0.1273. Okay, let's see what that gives us. So it's the same day, but it's now 3 hours, 3 minutes, 18 seconds, and I'm not sure what this final number is. Let's enter those in. 27, yep. So we want... Let me just check this is... Let me just check this is doing what I think it's doing. Month day. Okay. Okay. So it is doing what I was thinking it was doing, which is good. 3 hours, 3 minutes. I was happy. 3 minutes. This isn't doing at all what I thought it would do, which is interesting. And we want 18 seconds, which doesn't change much. But this is completely the dark side. I'm wondering if there's something wrong with the units here, or with the time frame that we're establishing. Let's try switching this to local time. Does that do anything? Oh, wait. Why did that PM appear there? I'm not sure. Maybe it doesn't change the input time. Okay. So, that's interesting. It's not done what I expected it to do. So, let's try the dip. 590878982. 59087 8982. We don't need this. 59087. Okay. 2020 August 26. What hour do we want? We want our 21:33. 21:33. Huh. This is almost exactly opposite to maybe what I would expect. 21:33. 24 seconds. It won't make much difference. So I said before that I suspected these bright things should appear at the start. So I'm wondering if this is exactly opposite to what I think. So if this is minus 12 from this, we end up with 9. I'm not sure. What could be happening here? It's not doing at all what I thought it would do. Which may be because Ceres, our TESS doesn't see Ceres in the same light that we're seeing Ceres right now. Let's see. Let's perhaps go backwards. So let's start with from time import date time. Where's it like this? Let me see. Hey Alan, thanks for joining. I'm not too sure how good the quality is. It's pretty choppy, but hopefully it's okay-ish to watch. I'm just fighting with various Python packages I haven't used in a while. Maybe I shouldn't try and use datetime. Let's maybe try and use the asteroid time. Let me see what formats this wants. Okay. So this wants a format. Oops. This wants a format like year 2020 dash month dash day, what were we? 26. T, and then we want hours, minutes, seconds. So 9:33. 33, 24. Okay, and then let's see. So we're going backwards to what we were doing before. And let's see if things are completely strange. So I'm going to plot a vertical line at the time that we got for when a bright spot should be there. And where has it plotted the vertical line? I think it has plotted the vertical line, because that vertical line is right there. Okay, so it went too far backward in time. That's not useful. So let's jump forward a while. Let's jump forward to 28th, we'll say. Okay. Have I been turning the wrong thing? Maybe not. So let's find a big bright spot. Oh, what extension am I using? I think I'm using Jedi. Let me see. Let me see. Yep. So I think Jedi is able to do these things. I think from memory I had some issues with 0.18. So I don't know. As with everything, nothing's ever quite as easy as what you would want it to be. So let's try and work out what's happening. So this may seem very messy and very unplanned, but this is probably the most real science stream we've done so far, because I've got no idea what's happening. And generally that's how my days go. I've got no idea what's happening. So let's pause time and try this again. August 28th, 13, 15, 32. August 28, 13, 15, 22. Okay. This one should hopefully be what we want it to be. Okay, so we've successfully plotted a line. And this line is more or less coincident with the bright spot. Which is making me wonder, this is what I would have expected, because this time frame here is just past the peak of brightness. And if we wind back the clock a little bit, then we're more face on to the bright spot. Okay, so then let's fast forward a little bit. But yeah, so that's peculiar, because this part I would think wouldn't be bright at all, because there's nothing too reflective on the surface. So let's keep rotating around until we find another bright spot. And then we can see what we see. Okay, so here's another bright spot. Let's record this time. Let's maybe save these as different variables. Okay, so we'll do a bright spot. These things have a name, these features have names, but I can't recall what they are. Crater. Okay. 28, 19, 28, 48. 19, 28, 48. 28, 48. We'll just call it bright 2. That's good enough. Bright 2. Good. Alright, so... Oops. Where does this line go? Let's give this a different color. This will be a nice orange color. Interesting. So this is... This is the start of the brightening peak. Is this object here? Okay, let's move forward in time a bit. Okay, so what is this point in time? So we'll call this bright spot 3. Bright 3. And what time is this? 19, 28, 48. 19. That can't be right. Have I mistaken something? This says which number actually changes. Ah, maybe I have mistaken something. I think this might be the number I should be looking at. What does this one change? This is peculiar. Why are there two things that change time? Why does this one change both, but this one doesn't? Okay. Which means I might have been recording the times wrong. Okay, let's try 20, 52, 44. 20, 52, 44. That was in the 28th. Let's try this again. Okay. And plot this on our graph as well. Let's make it a green color. Okay, so it's getting brighter. Okay. I guess that's brighter. So if I was recording times wrong, let's try this again. So this bright spot does then coincide with this, which is, I think, what we noticed before. So, yeah. So we've moved a day on from this point. So let's keep going forward a little bit until we've rotated this one out of the way. And let's check this time again. So 29th, 3404. We'll call this blank. Nine 30 00 what's this 33 27 blank. Okay. Alright, not sure what color that one will be. Purple. Okay. Huh. Interesting. So this secondary peak that happens does coincide with apparently nothing. I'm not sure what's happening there. So nothing is really there. Okay. So we have the brightest part. We move forward. So the brightest part, whoops. Oh dear. Where we were at 29. Yeah, so this is where we were. There's nothing really here. So let's rotate this around some more. So this side we were just looking at, which was apparently the second brightest part according to TESS, doesn't look much brighter than, say, this part here. So let's see about this part. We'll call this one blank 2. 29, 2, 43, and 2, 40, 45, 30. Yeah. If I'm... Okay, let me... I see now that the stream says it's got a green symbol, but it says no data. Oh, now it's gone back to a warning. That's good. Yeah, I'm not sure my internet's too cut out for doing this, unfortunately, which is what I suspected, but yeah, it's disappointing nonetheless. Okay. So... So this blank part is fainter than the other blank part. Interesting. But we still haven't found the faintest part yet. Well, let's see. So it was just before this peak, I think. Yeah, it was. Okay, so that's when we start to get brighter. That's when we get brightest. And this is when we have the second bump in brightness. And that's when we have... What was that? The decline in brightness. So the faintest part is around about... Whoops. Oh, jeez. This is very sensitive. Brightest part, second brightest. Maybe this part is pretty bright. Interesting. So when I came into this, I was expecting to find that this main bright peak coincides with the... Actually, jeez, too tricky to use this. Actually, let's go to where'd the Wikipedia page go? Okay, I think there is an unwrapped version of the land map. Okay. So we need to get our bearings again. So I think this is the first thing that rotates into view when we start getting brighter. Brightest is here. So this is what I expected would be the brightest. This point here, because it generally is the brightest in optical light. And TESS looks at most, or a lot of optical light. So that, I guess, makes sense. We have some bright spot here leading into more bright spots, leading into the brightest spot. And I guess the question is this part here substantially brighter than this part here? I guess it must be. Another option could be that since this image was taken, when was this image taken? Wikipedia is so very useful. So very useful. I use it all the time. So 2016 is when this image is credited. So this is 4 years before the data we're looking at from TESS. So it isn't perhaps unreasonable to suggest that maybe a new feature has appeared on the surface here. Or maybe it is just that this part is substantially brighter. Okay. But so far we've only looked at part of the picture, because this is like, we've only looked at the phase of one period. So if we zoom out again, and take a bigger chunk of points, you can see that this top peak is pretty consistent. But then it looks like the secondary peak is quite variable. So in this case, it seems to be brighter than the other cases. And if we keep going along, it's brighter again. I guess all of Ceres seems to be brighter there. And in this case, it's like nothing at all. So we have a very well-defined secondary peak in brightness, a well-defined secondary peak, and then just a slide off to nothing. And then a secondary peak again, another slide to nothing. And the peak emerges again in the data, and Ceres is gradually getting fainter. I'm guessing that's a a product of changing geometry between the Sun, Ceres, and the observer. Yeah, and then we have this, and it's back again. So where does it go? Where does it go here? Why does it just slide away? I'm not sure. If you have any thoughts while watching this, do leave comments, because this is just me pondering. If you want to throw your ideas into the mix as well, you're more than welcome. So there's, I guess, a few different questions. One question is, one fundamental question is this data reliable? I think it is. And I'm probably biased in thinking that because it was my data analysis pipeline which reduced this. So it removed all of the other sources so that we just have Ceres. So I think it is reliable. And I think this is a bright enough feature that it shouldn't just disappear in my data analysis. But then why would it reappear? So let's think through some possible scenarios. The scenario, I guess, that would be most exciting would be if, since this image was taken, there has been some cryovolcanism and has made like another spot that's kind of about half as bright as this one in this general area. So that would be interesting. But that doesn't tell us why it could just disappear and then reappear. So it is... How could you have that? You could have that if it were... I don't know, covered by some other activity, reemerge, covered again. I'm not sure. Yeah, this is tricky. For me, at least. There might be other astronomers who are more well versed at this thing, so it's not so tricky for them. But let's say that it's not. Well, it's the same problem, right? Even if we don't have a new bright spot that emerges here, just this part is reflective enough, then why does that reflective part get obscured and then return? So, one thing that you could do to try and get a better understanding of what's happening is by saying, okay, we know what this peak is, and we know that this peak should be like a constant brightness. It shouldn't change too much, we'll say. So then you also have it that this peak always comes in a pair with the secondary thing. So you could compare the brightnesses, the ratio of brightness at each point, and see what an outlier happens. So, yeah, so I guess we'll try that. What is the best way to do for that? Well, we have the peak, and we have that it repeats every 9 point something hours. Let's go back to the Wikipedia page. How often does Ceres rotate? Um, 9 hours and 4 minutes. Okay. So if we choose time here, right at the peak, 5909066. It's always so hard. I always can't remember these numbers. They get too long. 5909 66228. 66228. So we want to find the time. To find the time that's closest to this. I'm going to do that by saying argmin of the absolute value. So that happens at index 419. Let's take the median of let's call this end. We'll call it right end. Minus 1 through to plus 2. So we'll take the median. Maybe we should do more than that. Maybe not though, because I think that is at the. We get rid of the nice connecting lines and just have the data points. We can do say minus 2 plus 3. So we'll take those points. Oops. What? Why is it telling me nan? That's not what I want to see. Probably because there's nothing there. So I want this. Okay, that's better. So that is our bright index. What I should have done was find the corresponding dark part. So let's just put that in there. What I also should have done is start at the start. So let's do that instead. What is this? 59088.01404. 59088.10 or 0104. 0104. Okay. So what we're aiming to do is make an array of things. So we'll have a for loop very soon, which iterates over these numbers. So each time we'll add what is it? We'll add 9 hours. 9 divided by 24 plus 4 minutes in terms of hours, in terms of days. Okay. And this needs to be multiplied by I if we're looping over it. Call this second. Okay, now let's find the time that we want for secondary peak. Now this one's going to be a little more tricky. And maybe say maybe say around here. This is where we might take a wider median for this one. 590881342. 590881342. 3042. Is that right? 1344. Let's see. 1344. Okay. Call this S. We'll do the same thing. And we want, oops, what have I done? I'm missing a bracket somewhere. Nope. Yes. Which means this one isn't right. Add the bracket there. Okay, good. Yes. Okay. This one, actually maybe both of them. Is Python my language of choice? Yeah, it is. Most astronomers actually use Python. It's pretty useful. And it's mostly useful because astronomers have been using it. So there's a really good community in astronomy that builds packages that are really useful for science. Like one I've used, I think in the stream before, is something called AstroPy. And this thing has a lot of really important things in it. So, I mean, immediately we've got astronomical constants, cosmology. So if you wanted to do things with supernova or galaxies very far away, this is an extremely useful package. It means you don't have to go through and rewrite all of the cosmological models and put the parameters in, all that kind of stuff, which would be a nightmare. I/O has stuff to do with images, how we record images in it, so that's also useful. Modeling is also extremely useful for fitting stuff quickly. But yeah, C I think generally is better for large stuff. So I still know a lot of people who, if they're dealing with massive data sets or simulations, they do everything in C, C#, C+. But I haven't touched that myself. It looks kind of scary. Python does have C backends to stuff though, so in a way you're kind of using C for some of the operations. But Python's nice, user-friendly, perhaps not as efficient, or definitely not as efficient as C. But it's good, and the community around AstroPy and SciPy and that kind of stuff have made astronomy much easier, so you don't have to reinvent the wheel. So let's make a for loop and range. I don't know how many peaks do we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So let's go 20, do this. Then we'll make these, because I'm being lazy and dealing with lists, np.array b. Do the same for s. And then we can do how bright is S compared to B in an empty list. Good. Why? Why is that not doing what I'd want it to do? Probably because the indexes are being weird. It is being weird. 0, 0, 0, 0, 0. Why is that the case? Why is an increasing number? I guess second end is always 0. Hey, great. Let's thanks for joining from Germany. Stargazing walks are always the best kinds of walks. I like going on those ones to think about things, or go for a run at night. It's always nicer. I don't know. Nighttime with stars is pretty nice compared to the day. Yeah, I think it's probably bias or expected of me to be an astronomer, but stars are pretty nice. Like sunset to nighttime is always good. So why is my index broken? No clouds. That's even better. It's that's the fate we all are subject to. It's just always clouds. Yeah, I was supposed to observe with some telescopes a few weeks ago, but instead I got to play around in snow, which was, I think, perhaps a better trade. No lights. That's also really good. So yeah, it's I live in Christchurch in New Zealand, so it's not too big of a city, but even still, there's a lot of light pollution here, and you have to go quite far away now to get dark skies. But luckily, there's like a big dark sky reserve not too far away. Things like 3 hours driving. So it's quite nice to get away from the lights every now and then and see, well, I guess, all of the stars in the galaxy above us. It's a good way to remind, or at least for me, to remind myself that astronomy isn't just bugs and computer scripts. So speaking of bugs and computer stuff, why is this not working? It's probably something very obvious that's staring me in the face, but I'm not seeing it. Okay, that looks fine. Oh, brackets are important. So I was subtracting a number, and then I was just adding a number. I should have added the number I was subtracting. Okay, that works now. Good. There's always something obvious that stares you in the face, but you just don't see it. Okay, let's try this again. So how bright is the second bump? Oh, oh no. Why is this not working now? What? Oh my gosh, what is going on? So this is right. This is getting me indices. Good. Bright. Oops. Bright. And that's also working. Good. So then why isn't this working? The same perspective. I've seen the trees move around while walking, but the stars staying the same. Yeah, that is a very good point. Stars are just so incredibly far away from us. It's almost unbelievable how far away they are. And that is, of course, one of the reasons why people resisted the idea of the Earth moving, because they said, well, if the Earth moved around the Sun or some other object, then surely we would see the positions of the stars change across the year. And that would be right, of course, that we would see them change across the year if they were very close. But they change like just a tiny, tiny fraction of a degree. So, you know, they change, but to a point where we can't perceive their change. Telescopes like Gaia, which look for parallaxes, can perceive a change, but they're like incredibly precise and in space. So they're pretty useful. Yeah, they are incredibly far away. So I found out what the problem was, because I was trying to add to a list. I need to make what I'm adding a list element. So this should work now. Good, it does. Alright. Let's try this for a third time. That looks pretty consistent. So it's 98% the brightness. Some slight wiggles. Let's also record. Let's also record. Let's also record halfway between these two. I want an integer division here, so I don't end up with an error telling me that indexes can only be integers. And let's plot this with time in the mix as well. 46. Okay. Do that. So, what do we have here? Some jumping. When was the stuff that we looked at? So this was 59091.5. 5. Yeah, so this is pretty much it. So, yeah, so it does look like an anomaly. So it kind of bounces around this kind of average, and it dives down for this, and then bounces around some more. Interesting. I think maybe I should also check that these are going where I think they're going. So we'll do the same thing as we did for end, but we'll do it for these two. Sometimes autocomplete is too useful and it doesn't do what you want it to do. Okay. Should be that. Let's grab these from before. And we want these to be at bright, or what I call BI. Oops. That line there. Is this doing what I want it to do? Not quite lining up, is it? Not quite. Interesting. Wonder why it changes a little bit. Maybe some weird relativistic thing. What you're looking at? We're looking at a light curve of Ceres. It's a dwarf planet in the asteroid belt. And this light curve was recorded by the Transiting Exoplanet Survey satellite. And we have a few days of data, so this is all of it here. So we're trying to work out why it has this shape. So the first thing we did was try to see if these bumps and wiggles matched up with surface features we see on Ceres, which left us with a bit of a puzzle because this big bump matches up, the second bump maybe doesn't match up. So the question is, does this bump exist in previous images? Is it new? Is it a feature we haven't, or that I don't know of? But at the moment, we're trying to look at this bump is generally pretty regular, and then it seems to just kind of disappear for at least one, or say for this one and for this one. So not sure why it disappears. So we're just looking at the ratio. We're trying to look at the ratio of this top peak to the second peak through time to see if the ratio changes. See if how maybe significant this bump change would be, to try and get rid of like this overall trend of shifting brightness. But I'm thinking that maybe this isn't quite precise enough. But it seems to be okay. Maybe this data doesn't agree that let me do something I should have done before. So I put signal import peak. What is it called? Something to do with peaks. Find peaks. There we go. Find peaks of power, I guess. That's bad. So this thing here is trying to find some peaks in the periodogram, so I can use what TESS thinks the period is actually. So it's the albedo of Ceres. Exactly right. Yeah, so when Ceres is brighter, or has a bright spot pointing towards us, is when we get this bright peak. When the bright parts are pointing away from us, we get this fainter part. But it's interesting because it looks almost like this fainter part should more or less be the same as this part from images. So why does this bright part kind of exist, and why does it kind of change its shape a little bit? So let's go back to this. Does this get the peak we want? 2.9. It does. 2.9. It's probably that one. There's another one here, and then so this is -2, which is 99. So if we do frequency of 99, oops, frequency of, yeah, Jupyter is pretty good. I also used MATLAB in undergrad, but then changed since pretty much everyone in astronomy uses Python. It's free, and it has a lot of useful things in astronomy. So I started using what everyone else was using. It seems to work pretty, well, it does work very well. So it depends, of course, what you're using it for. I know if you're doing something like engineering, then MATLAB is very useful. Oh my goodness. Oh, sorry. That's the trouble with doing streams, is that sneezes can appear, as well as fighting with the internet. Okay. Or, yeah, my internet, not necessarily with viewers on the internet. This still doesn't seem to line up perfectly. I guess it's okay. I guess it's okay. Let's see if the second index is also okay. Yeah, I guess this is okay as well. Not really, though. Why does that move? Why are these not the... Why does this move? So there's like a pretty consistent shift. And then the peak happens. Why is that? That shouldn't be the case. It should be just a shift according to the period. Not sure. Maybe if I just do a hack solution for now and just, I don't know, add 2 add 2 to each of these and say that fixes the problem for now. does that kind of fix the problem? Nah, it delays the problem. How peculiar. Yeah, I'm not sure what's going on with that. It should be pretty consistent throughout the entire thing. But it changes a bit. But yeah, this is... this says, or at least to me, this indicates that... Well, for one thing, look at the change in percentage that we're looking at. So it's kind of bouncing around at an average of 0.986%, and the dip is 0.004% or something like that, 0.005%. Oh, sorry. That's not right. It's bouncing around at 98.6%, the same brightness. And then it dips by 0.4%. So that's quite a minuscule dip, but it is measurable. And this coincides with between 5091 and 5092. So between these two values. Yeah, so it's this one that we were looking at before. Just kind of slides off. It's interesting that this one is of comparable brightness. Yeah, I'm not sure. This could just be an anomaly. The data is bad at that point. Or it could be something else. Yeah, I'm not sure. I'm really not sure. So this is the problem with messing around with data on objects you don't really know about. Is I could concoct any number of wild and fantastic theories for why this happens. It doesn't mean any of them are remotely correct or are remotely close to being true. So I'm wondering if I need to be happy with this for now and talk to some people who know what's actually going on or have a better understanding of minor planets and see if they have any thoughts on what's happening. But yeah, so that's, I guess, yeah, it's been going for a while. I probably should get on doing some other things. So if you have any other questions about anything, of course, feel free to put them in the chat now. But we'll probably wrap up relatively soon. While we're waiting for questions that you may have, perhaps I'll show this one thing that I stumbled across yesterday, which I should have seen a long time ago. I'm not sure how I missed this. It's the sharpest photo, or so-called sharpest photo ever taken of Andromeda. Where are you right now? I'm in New Zealand, in Christchurch, New Zealand. So I was in America, in Baltimore, doing work at the Space Telescope Science Institute and then Johns Hopkins University. But now I'm back in my home country and enjoying being back. In lockdown for the moment though, but hopefully that will be over in the coming weeks. So, this is a picture of Andromeda, or lots of pictures go into making this picture. And the really cool thing about this is that you can just keep zooming in. And it's made like Google Maps, so the more you zoom in, the more it will refresh. So these stars are just bright stars, and if we keep zooming in, I wouldn't badmouth Baltimore too much. I guess it's kind of, I didn't really get to experience Baltimore too much either. I was there for most of the time during the pandemic, so I was being careful and didn't go out too much and didn't go to too many places. So I probably don't have the best impression of Baltimore because of that. But yeah, it does. That's not to say it doesn't have its challenges. It definitely has pretty substantial challenges, which I wasn't quite happy with, particularly like homelessness and things like that. So, you know, these things are not so prevalent in New Zealand, so it's I guess it has a nicer feel for me at least, and it has mountains close by, and I really like mountains. Anyway, we can keep zooming into this map, and you see like there might be some things appearing in, and it just kind of looks like grainy, sandy stuff. If we keep zooming in, what you soon realize is that, oh, this isn't just like detect a noise. These are individual stars. And each one of these stars is like somewhere like the sun, or at least these white ones are probably places pretty similar to our sun. The red ones are maybe really big stars or really small stars, one or the other. These blue ones are pretty young, massive stars. And you just can skim over it, and it's like, how many stars are in this single frame? Probably thousands. And then, like, for context, you can zoom back out again, and it's just one tiny fragment of this part of the Andromeda Galaxy. So we can zoom in like over here. Give it some time to load with my horrible internet. What do we find? You know, that there are still stars everywhere. It's so you hear people say like, oh, there are like hundreds of billions of stars in a galaxy. Cool. I've said that to lots and lots of people. But it makes no, you know, that's not a number you can process. What's a million? It's hard to even visualize what a million is, but a billion, that's even harder still to understand. So 100 billion is just inconceivably large. And this is, I think, the first time looking at this, I realized 100 billion is a lot of stuff. Like, you just pick any part of this galaxy, you zoom in, and there's just stuff everywhere. All of these things probably have planets orbiting around them as well. You know, and then you can play the game of, oh, maybe there's life on some of those planets. And then, of these 100 billion, how many have things living on them? How many of them have geological processes, at least, like interesting planets? So it's just an unbelievable amount of stuff. So one thing to notice, though, is right out on the edge of the galaxy, it's not so dense. You can see there's like some space between the blurred out pictures of stars. But if we... So this is on the far edge. Yeah, I agree completely. It's, yeah, it's... As an astronomer, people think I have an idea or an understanding of big things, but the reality is you just grow numb to it. It's just, oh, it's, you know, the universe is 13 billion years old, cool. The objects I look at are hundreds of millions of light years away from us, cool. Yeah, it means... But the reality is, I don't actually understand what that distance means. I don't think it's possible to understand what that distance means. It's just like, it's just, okay, it's a number. you put it in context of this number is normal for a supernova or for a galaxy or something like that. It's not an actual conscious processing of what that stuff is. So in the center of the galaxy, or near the center of the galaxy, you can see there's like overlapping stars are all blurring together and making like a continuous blob. So this is incredibly dense, and if we zoom out again and jump to another part of the outer part of the galaxy, then we can see that, you know, stars are kind of individual things. We can see them by themselves, and they all kind of float around in space, isolated. So the interiors of galaxies are far more dense than the exteriors of galaxies. And that's one of the many cool things that you can see from this. And I guess another cool thing we can look at is like these big dust lanes in the galaxy, so nebula. And I should also post this in here if anyone wants to look at it themselves. So you'll notice the stars here actually seem to be a lot redder than in the other parts. That's probably not a consequence of there being no blue stars. It's probably a result of red light passing through the dust a lot easier than blue light. So you can see physics in action here. Stars are being obscured by all of the dust, and the redder stars can make their way through the dust a little bit easier, or their light can make it through. So this is a pretty cool, a really cool image. Definitely a lot of fun to be had just roaming around this and trying to make sense of a galaxy of stars. But this again is like only a fraction of the Andromeda galaxy, right? So this is, say, at most 1/2 of the galaxy. So it's probably a quarter of the galaxy-ish. Titan scattering. I'm not sure what that is. Let me... oh yeah. Yep. Yep. It's been a while since I've... You're exactly right. That is the kind of scattering that goes on. Yeah, it's just all of the dust and all the stuff suspended in space, scattering and blocking light, getting to us. So it's pretty cool. I'm planning on making a video on this sometime in the future, because it's pretty neat, and we can go through like some of the main things of the Andromeda galaxy that we can see in this image. But this is a pretty old image as well, I think, so it's not new. I just haven't seen it before, or I've seen it and then just passed by it. So it's really cool. Okay, so I think I'll wrap the stream up there. Or no, we've got a question. How large of a star would you say visible in that image? km. Probably, well, based off the colors, I would say that the limit is probably K stars, though that might be wrong. I'm not too sure as to the what Hubble's sensitivity is for such a close object. So I think Hubble can go to something like 22nd magnitude, and I'm not sure how bright. I'm not sure how bright these M stars would be at the distance of Andromeda. But if you could see M dwarf stars, then they should dominate the image. There are by far more small stars than there are large stars. So, as well as there being a lot of stars here, this is probably only a fraction of the stars, because you can still see these little blurry faint things in the background that Hubble just isn't powerful enough to see or resolve. You'd need a bigger telescope to do these things. But that's a good question. It's one I'll need to investigate more before making the video. So thanks for that point. I'll remember that. Yeah, I don't know. Hopefully we'll be able to. Probably not us, but hopefully sometime in the far future, our descendants will be able to explore galaxies or even just neighboring stars. I'd settle for neighboring stars. Fermi paradox: would you expect to be able to detect civilizations' radio waves when they have to be transmitting at the intensity of a star? Fermi paradox is a very good question. I don't have any particularly new or unique view on this. I think what it probably tells us is the unfortunate thing that... just fighting with my mic, sorry. I think what it tells us, in a pragmatic sense, until we get more evidence, is that complex life like us, and intelligent life like we claim to be, is very hard to get in the universe. But that said, you do need to have, just like TV radio signals, most of them don't pass through the ionosphere of Earth, so they don't make it out of the Earth's atmosphere, so they don't make it into space. And when they do, they're not really directed there, so they're not the most powerful signals. But we do have radio telescopes now that are so big and so sensitive that you could see, if you directed your telescope and looked for long enough at nearby stars, you might expect to be able to detect radio signals from the nearest stars, from planets orbiting those nearest stars. But of course we haven't really done a systematic search yet. There's the SETI Institute, which uses radio telescopes to look for technosignatures around distant stars. But, space is very big, and SETI's been going for like a couple of decades now, and I think it's only effectively like a drop of water in an ocean is what they've looked at so far. So I think probably life is generally pretty easy to get started in the universe, but we still need evidence to see if that's true. Complex life, I think, is much harder to get to. And then intelligence, there's no real reason why intelligence should be useful. There's I guess there's a threshold, right? Because for say a rat or something, does being smarter than the average rat really help that rat in surviving and reproducing? It's not clear. Maybe not. But clearly, once you get past a certain point of intelligence, being smart is very useful, and you can dominate the entire global ecosystem and threaten its collapse. But it's still not obvious that intelligence is a necessary end result of evolution, because otherwise maybe you would expect to see many more intelligent creatures here on Earth. Like the smartest parrot is maybe as smart as a toddler or something like that. Dolphins are kind of as smart as a child, perhaps, on the way we rate smartness. So, they're intelligent, but they're not super intelligent, I guess. In comparison to us, they're still quite lacking. And then our closest relatives, they also have some level of intelligence, but they don't have the level that we have. So it's seems very tricky for life to become intelligent. So, it's that's a very long-winded answer to my thoughts on the Fermi paradox, but I think we probably haven't seen anything, because there probably isn't much there. And if there is stuff there, then they're probably very, very far away from us, right? Because the closest star system to us is Alpha Centauri. That's 4 light years away. So a backward and forward communication with them would take 8 or so years to do. And that's, there's no real good candidates for habitable planets around Alpha Centauri. So if you went further away, say like the closest 100 light years, maybe there could be something. But then a round trip communication with them is 200 years, and not really much can be said. Hi, how are you? Good, thanks. 200 years. That's a pretty difficult thing to do. Of course, you'd send much more information-dense stuff, but it's like if we sent a directed signal out into space now, and waited for a reply, we would need to wait hundreds of years before, hundreds if not thousands of years actually, to see if we would get a reply. And even then, they might think like we do and think, oh, maybe we shouldn't broadcast ourselves to the universe because there could be some big angry alien species out there that wants to find us and take our resources or something like that. So, you know, I think, and I guess the last point on this, maybe I should make a video on the Fermi paradox at some point, but I think the last point on this is that the Earth and the solar system are actually relatively young as far as the universe is concerned. Because the universe is 13 billion years old, or 13.7 billion years old. But that doesn't mean you could have formed life at the beginning of the universe. You needed time for galaxies to form, for stars to form, for stars to process all of the materials that we're formed from. So it's only kind of in the generation of stars that the sun is that you start getting enough materials that you can make pretty complex rocky places, and from those rocky places people, or some kind of life and intelligence. So if there is life out there, you know, it's probably on the order of plus or minus at most 1 billion or so years, which is, I guess, a lot of time to us, but not necessarily a lot of time. And then there's just the added random factor of if intelligence actually emerges in that as well. So, you know, that's not a clear answer, I'm afraid. That's kind of, it's a very multifaceted problem. Yeah, the Earth is extremely diverse in material, and that is just the result of like billions of years of stars living and dying and exploding and colliding with each other to create all of the materials that we're made from. So, you know, it takes a lot of time to get through the universe and process like 1% of the hydrogen that exists into other stuff. So, yeah, it takes time, and it's unclear to me if intelligence is necessarily useful for life. But that doesn't mean to say we can't perhaps find a way to go around the universe and throw life in places that are lifeless. That could be pretty cool. But yeah, for now, we're alone, and it looks like it'll be that way for a while yet. But, you know, I do hope, as many other astronomers hope, that that life does find a way, and finds a way to contact us. But, yeah, that's probably where we're gonna wrap things up for today, on that rather dramatic note, I guess. Thanks for the questions, Biggie. They're very, very good questions. Yeah, so for everyone who's joined, thanks for watching. Hopefully the internet wasn't so bad, and hopefully it was vaguely interesting seeing, I guess, my thought process of how I approach data and try and make sense of data. So we'll keep working on Ceres stuff. We might have some more science streams in the future, but it's kind of tricky because the internet's not so good here. That was a really good thing of Baltimore. It had fast internet compared to where I am at the moment. So yeah, if you watch this later on, have questions, leave me questions wherever you want. Contact me on Twitter if you want. I'm usually checking Twitter. Yeah. However many you've got, I'll probably be able to answer at least some of them. So, again, thanks for watching, and see you next time.